this class is about this equation and potentially this equation. This is unforced or free vibration. This would be force vibration. And what we want to do is to try to see how the eigenvalue problem, solving the eigenvalue problem, helps simplify the solution of these differential equations. We've already seen how the eigenvalue problem arises. The eigenvalue problem is of the following form. Something like this, plus k times v equals 0, or kv equals omega squared mv. Right. This comes from assuming that the solution to x is of the form some amplitude times some vector times sine omega t or cosine omega t. Okay, so now that we have this eigenvalue problem, we can solve it. We sort of saw how to solve these eigenvalue problems, but how does solving these eigenvalue problems help us? This is the so-called generalized eigenvalue problem. N eigenvalues. We call them omega I square. These are the eigenvalues. N eigenvectors. P sub I. So that we have k times vi equals omega I square m vi. Right? So there are n solutions to the problem, and each of those satisfy this equation, where v is an n by 1 vector, and omega I is a scalar, and k and m are n by n symmetric matrices. K comma m are n by n symmetric matrices. Okay. Where n is the number of degrees of freedom in the system. Okay. So x is also an n by 1 vector. Okay, so these are n eigenvalues and n eigenvectors that satisfy this eigenvalue problem. And what we would like to first show is that these eigenvalues and eigenvectors, in particular the eigenvectors, satisfy a particular property that dramatically simplify the solution of the differential equations. In particular, they satisfy this property called orthogonality. The eigenvectors vi satisfy the ortho and orthogonality properties. With respect to matrices M and K. What do you mean by that? If you take a vector vi and take the transpose of it, multiply with the matrix M, and then multiply that with vector Vj, where Vj is not equal to Vi. In other words, it is not the same vector. I is not equal to j, and that is equal to 0. And similarly, Vi transpose K Vj is also equal to 0 for I not equal to j, for I not equal to j. This is called the orthogonality with respect to M and K. You also have the sort of normal orthogonality, which you guys probably learned in a sophomore vector mechanics class. Normal orthogonality is just Vi transpose Vj equals 0, not generally true for systems like this. Okay? This may be true sometimes in special cases, but not generally true. This is just saying the vector Vi and the vector G are perpendicular. That's normal orthogonality. That is, this property happens to be true for the sort of not quite generalized, the normal eigenvalue problem, the symmetric matrix, the eigenvectors for that satisfy this property. But here we have a generalized eigenvalue problem with M and K, and it turns out that the eigenvectors satisfy this modified orthogonality problem, or the property, or the orthogonal with respect to matrices M and K. Okay? So you'll first prove these properties. In other words, this and this. And then, once we prove this, we will find that this orthogonality property helps immensely in simplifying, solving the differential equations. Okay. So what we're building up to is a dramatic simplification of these two equations, okay, using the solution to the eigenvalue problem. How do we simplify the eigenvalue problem? We are going to use the orthogonality property. But first, I'm going to prove the orthogonality property. With respect to M and K. So let's consider Vi comma Vj with I not equal to j. In other words, they are two different eigenvectors. And then, because they're eigenvectors, they of course satisfy the eigenvalue problem, namely kvi equals omega I square m vi, and kvj equals omega j square m vj. Let's call this equation 1, equation 2. This is just by definition, by the fact that they are eigenvectors, the eigenvalue problem. Next, we want to prove orthogonality. In other words, we want to say Vj transpose kvi equals 0. So we want an expression that looks like Vj transpose kvi. So let's multiply these equations by the appropriate things so that we get those expressions. So multiply, or let me just say do Vj transpose times equation 1 to get Vj transpose kvi equals omega I square, which is just a scalar, so it can go outside. Vj transpose m vi. Okay, that's equation number 3. Similarly, we can do the I transpose and equation number 2 to get to get the following thing, namely Vi transpose K Vj equals omega j square Vi transpose M Vj. It's going to be equation number 4. Now, notice that these two equations have the i's and j's in opposite order. It would be nice to sort of get them in the same order so that you can sort of subtract them and cancel out terms perhaps and so on. I remind you of the expressions for taking the transpose of products of matrices. So if you have two matrices A and B, the transpose of that matrix is B transpose A transpose. And then if you have three matrices A, B, C, and transpose of the product of A, B, C is going to be equal to C transpose B transpose A transpose. In other words, the order of the product becomes backwards. And the reason I sort of brought this up is that we want to reverse the order of i's and j's here. And one way you can do that is take the transpose of this equation, in other words, transpose on either side. And then if you do that, Vi transpose K Vj will be sort of analogous to ABC, and then if you take the transpose of that, the j will come to the first place, K will remain as such, and I will go to the last place. Okay, so let's do transpose of equation 4 on both sides. What we mean by that is, so we do Vi transpose K Vj whole transpose equals omega j square Vi transpose M Vj whole transpose, and then just by the ABC whole transpose relationship that we just talked about, we get Vj transpose K transpose Vi transpose transpose, which is just Vi. Okay, transpose of transpose is just Vi, and then we get omega j square Vj transpose. So the last one becomes first, M transpose Vi transpose transpose, and that becomes Vj transpose K transpose Vi equals omega j square Vj transpose M transpose Vi. But this equation can also be simplified further using the fact that K and M are symmetric. K and M are symmetric. This just means that K transpose equals K and M transpose equals M, right? Symmetric just means that if you have a matrix like so, if you bring this here and bring that out here, in other words, if you reflect about the diagonal, that's basically transpose. That's what you mean by symmetric. Okay. So this equation becomes Vj transpose K, because K equals K transpose Vi, equals omega I square Vj transpose M Vi. Okay. Let's call this equation number 5. And then we have equation number 3. Recall 3, I'm just going to copy it over from the other side of the board. Equation number 3 is actually has the same thing, the same order. Vj transpose K Vi equals, this is omega j. I should have said omega j, not omega I. Okay. This is omega j. But equation number 3, in fact, has omega I square Vj transpose M Vi. So this is equation 3, just rewriting this here. Okay, so these two equations are almost identical except for the omega j and omega I being potentially different. 3 minus 5 gives us Vj transpose kvi minus Vj transpose kvi equals omega I square minus omega j square Vj transpose km vi. Okay. This gets cancelled. This implies omega I square minus omega j square times Vj transpose m vi equal to 0. This implies Vj transpose m vi equal to 0 if omega I not equal to omega j. Okay? In other words, if the natural frequencies corresponding to the ith and the jth modes are different, then this equation follows from this equation. It turns out that even though this orthogonality, so this is the orthogonality property, it turns out that even though this proof, we're going from this step to this step, requires omega I not equal to omega j, turns out if omega I happens to be omega j, in other words, two modes have exactly the same frequency just by chance, which is rare but possible, it turns out that the situation that we have is that we have a lot of eigenvectors. In particular, there is a plane of eigenvectors that correspond to those two eigenvalues that are equal, and you can always select eigenvectors in a manner that they are orthogonal in this manner. But for now, we'll just go with this proof where you say that this equation, this orthogonality, follows from this orthogonality property. To prove Vj transpose kvi equal to 0, what you do is you do 3 divided by omega I square minus 5 divided by omega j square, and that will give us 1 over omega I square minus 1 over omega j square times Vj transpose kvi equals Vj transpose m vi minus Vj transpose m vi. These two get cancelled, that's equal to 0. And this implies Vj transpose ki equal to 0 if omega I not equal to omega j and omega I not equal to 0, omega j not equal to 0. Right? So the only way you can do this division is if either of these two things are equal to 0. Okay, so that's the proof. This is orthogonality of the eigenvectors with respect to m. This is orthogonality of the eigenvectors with respect to k. So this is again orthogonality. Okay, so what we've done just now is we have proved Vj transpose m vi equal to 0, Vj transpose k vi equal to 0, given I not equal to j. Okay, so that's what we've proven. Now let's see, use this to simplify the ODE. Okay, so we have this equation, M Xdotdot plus K X equal to 0, defined. The matrix V, capital V, which is all the eigenvectors arranged as a column. Okay. So column number 1 is the first eigenvector, column number 2 is the second eigenvector, and so on. Column number n is the nth eigenvector. We're going to call this sort of uppercase V. Okay, this is an n by n matrix. And then what we do, well, before we actually use this matrix, we want to understand the properties of this matrix. Properties of V, V transpose MV equals. So V itself is that thing, and V transpose MV is really, this is V, this is M, this is transpose times V1, V2, etc., something like this, right? So we have this equation. Let's simplify this a little bit, or this expression. Let's simplify this a little bit. Let's just retain this thing, V1. We can bring the transpose inside, but let's wait until we do that. So we have this stuff. This is equal to this. We can take the product inside. So what we have is MV1, that's the first column, MV2 is the second column, etc. The first column is MV1, second column is MV2, etc. like that. And then we can do this, the whole transpose, which is going to be, we call the first column is V1, second column is V2, and so on. And if you take the transpose of that, what will happen is the first row will be V1, the second row will be V2, and so on. But it won't be V1, but because V1 is a column vector, so the first row will be V1 transpose, the second row will be V2 transpose, etc. Something like that, times M V1, M V2, etc. Okay. So let me write a couple of more terms so that it's clearer. V3 transpose, etc. Then this will be M V3, etc. Okay. And then I'm just going to erase this to do the simplification right here. So that expression becomes equal to a square matrix of the following form. The first element is going to be this row times this column. This is going to be the 1, 1 element. The 1, 2 element is going to be this row times this column. The 1, 3 element is going to be this row times this column, etc. So you can write that down here. I'm just going to draw a grid here so that it's easier, but I'm just going to do a little bit. So it's going to be V1 transpose M V1, V1 transpose M V2, V1 transpose M V3, etc. This is going to be V2 transpose M V1, V2 transpose M V2, V2 transpose M V3, etc. It's going to be V3 transpose M V3, V3 transpose M V1, V3 transpose M V2, things like that. So we'll have, right. So what do we have? We have a matrix with diagonal elements equals V1 transpose M V1, V2 transpose M V2, V3 transpose M V3, etc. And the off-diagonal elements are of the form Vi transpose M Vj, where I and j are not equal. Okay, so these off-diagonal terms are actually equal to 0 by orthogonality. They're all 0, the off-diagonal terms. And the diagonal terms, well, they may be 0 potentially, but in general they're not equal to 0. So we just leave them as it is. So we say this equation or this matrix is of the form M11 bar, M22 bar, M33 bar, etc. That's a diagonal, and the off-diagonal terms are 0. So huge 0. And all you have is a diagonal matrix. We're going to call this matrix M bar, okay? Which is, recall how we got this thing. M bar was this V transpose M. Okay? So this is incredibly important. This is perhaps the most important result in multi-degree of freedom linear vibrations, which is that you take the original differential equation, you set up the eigenvalue problem, you solve the eigenvalue problem, get the eigenvectors, v1, v2, v3, v4, v5, etc. Arrange the eigenvectors in the form of a matrix where each column is a eigenvector, and then you do v transpose mv using that eigenvector matrix, v transpose mv, where m is the mass matrix, v is the matrix of eigenvectors, and then you get a different matrix M bar, but this different matrix M bar is a diagonal matrix. This is incredibly important. Right? So the off-diagonal elements are 0. Because we just proved Pj transpose M vi equals 0. Okay. And then this is a diagonal matrix. This is, in some sense, most important. Okay, this is an important result. I'm going to write down another important result. Now you can guess that similarly, the matrix V transpose K V will be equal to this thing, like we just did. And that's going to be equal to this matrix, just like M, V1 transpose K V1, V1 transpose K V2, etc. V2 transpose K V1, V2 transpose K V2, etc. Right? So it just goes on for a while. I'm just putting dot, dot, dot. And that results in all the off-diagonal terms being equal to 0. Off-diagonal terms are all 0. And only the diagonal terms remain. So this now is going to be equal to some diagonal matrix with V1 transpose K V1, V2 transpose K V2, V3 transpose K V3, etc. And then everything off diagonal equals 0. And we're going to write this as K11 bar, K22 bar, K33 bar, etc. with off diagonal equals 0. Okay? And this matrix we're going to call equal to K bar. It's a diagonal matrix. This, again, recall, this is equal to V transpose K V equals K bar, which is a diagonal matrix. Again, this is super important. Now, K11 bar is given by V1 transpose KV1, K22 bar is V2 transpose KV2, and so on. That's something we want to go over. Thus, we have shown that V transpose M V equals M bar a diagonal matrix. V transpose K V equals K bar a diagonal matrix. M I bar, which is the diagonal element, ith diagonal element of M bar, and KII bar is equal to ith diagonal element of K bar, which is given by this thing, and that's equal to VI transpose K V J. Okay. Sorry, VI transpose K VI. And then, so why did we do all this? We want to really solve the ODE. Let us go back to the ODE, which is this. We are still doing unforced or free vibration, but nevertheless, that's fine. So if you have a differential equation like this, in some variables x is an n by 1 vector, do a change of variables from x to eta, also an n by 1 vector, where eta is given as follows. Eta is given by the following equation: x equals v times eta, where v is the eigenvector matrix. It's a matrix of eigenvectors. Let's call this equation number 1, equation number 2. You want to plug in equation number 2 and equation number 1, for which we need to compute x double dot. X double dot, if we use this, will be equal to v times eta double dot. V is just a constant, it's a constant matrix. Eta is a function of time, because x is a function of time, so we have this relation. So what we have is m times v eta double dot plus k times the eta equal to 0, right? So this is x double dot, this is x. We can multiply, let's call this equation number 3. We do v transpose times equation number 3, and we have v transpose m v eta double dot plus B transpose K V eta equal to 0. And this, of course, is equal to M bar. We've just established that this thing is a diagonal matrix times eta double dot, plus this thing is another diagonal matrix called K bar equal to eta. Okay? This is a very important result again, which derives from the previous thing that I said was the very important result, which is that this thing equal to a diagonal matrix and this thing equal to a diagonal matrix. And using that fact, namely that B transpose MV and K transpose MV are diagonal, we have converted this differential equation with M and K being not quite diagonal to this differential equation where M and K, in particular M bar and K bar, are diagonal. Okay? M bar and K bar are diagonal, and let me just write that. M bar and K bar are diagonal. What this means is that you take n differential equations that are coupled, and this system, it turns out, is uncoupled. It is n uncoupled ODEs. We'll see in a minute how that comes about. So we've just shown that our differential equation reduces to, or differential equation M Xdotdot plus Kx equal to 0 reduces to M bar eta double dot plus K bar eta equal to 0, where M bar equals M11 bar, M22 bar, etc. And K bar is K11 bar, K22 bar, etc. Right? So they're diagonal matrices. And this implies we can rewrite this equation. Right? So M bar eta double dot is going to be equal to M11 bar, this whole matrix, times eta 1 double dot, eta 2 double dot, etc. Eta 1 double dot, eta 2 double dot, etc. And that just gives us M11 bar, eta 1 double dot, M22 bar, eta 2 double dot, etc. Similarly, K bar eta is going to be equal to this column matrix K11 bar, eta 1, K22 bar, eta 2, etc. Okay? And what we get is when we plug these two things into this equation, we get n equations of this form. All this implies M11 bar eta 1 double dot plus K11 bar eta 1 equal to 0, M22 bar eta 2 double dot plus K22 bar eta 2 equal to 0, M33 bar eta 3 double dot plus K33 bar eta 3 equal to 0, dot, dot, dot. In other words, we'll have n such equations if we have an n degree of freedom system. But the important thing is that each of these equations is decoupled from every other equation. The eta 1 double dot equation does not have eta 2, eta 3. The eta 2 equation has only eta 2. The eta 3 equation has only eta 3. So the big result is that if you start from a system of differential equations of this form, where m is not diagonal and k is not diagonal, and each equation has x1, x2, x3, etc. In other words, they're all coupled. This is coupled, possibly coupled. You
give rise to or convert that differential equation into this form where m bar and k bar are obtained by v transpose mv and k, v transpose mk, this is uncoupled or decoupled. Okay? And this is incredibly important because what we've reduced it to, reduced the coupled n differential equations to n one degree of freedom equations. This equation is just like M Xdotdot plus K X equal to 0, where X is a scalar, right? This is just one, it's literally a 1 degree of freedom system. This is another 1 degree of freedom system. This is another 1 degree of freedom system, etc.
So thus, we have reduced the possibly coupled n degree of freedom system M Xdotdot plus Kx equal to 0 to n uncoupled 1 degree of freedom systems of the form n I bar eta I double dot plus k I bar eta I equal to 0. This equation can be rewritten as just divide through by MII, assuming it's not equal to 0. And we can rewrite this into this form. Where omega I equals square root of kii over mii are the n natural frequencies. So let's do a summary of free vibration for n-DOF systems. We have, let's say, given an ODE of the form M Xdotdot plus Kx equal to 0 with initial conditions the position are given, the velocity are given, and what you have are, you solve the eigenvalue problem, solve for omega I, vi satisfying k vi equals omega I squared and vi. Those are the eigenvalue problems. Once you have that, this is step 1. Step 2 is construct the matrix V equals V1, V2, etc. And then M bar equals V transpose and V. K bar equals V transpose and K. V transpose KB.
implies these are now going to be diagonal matrices. Compute MII bar equals VI transpose and VI. KII equals VI transpose K VI. Step 3, well, let's say this gives us these equations and one-DOF equations of the form eta I double dot plus K II bar divided by M II bar eta I equal to 0. Solve for eta I. Eta I of 0 is actually going to be, sorry, not eta of 0, eta of t, if you remember, is going to be equal to eta I of 0 times cosine omega I t plus eta I dot of 0 divided by omega I times sine omega I t. This is actually a solution to the ODE, solution to the one-DOF system. Okay, it's a free vibration problem. This is what we did in the first few lectures. But what is unknown are the initial conditions. Step 4, or what is it, step 3, to get eta of 0 and eta dot of 0, what do you do? Just use the fact that x equals v times theta. In other words, eta equals v inverse x implies eta of 0 equals v inverse x of 0 and eta dot of 0 equals v inverse x dot of 0. Right. So this gives us initial conditions. Then once you have the initial conditions, you can plug it into these equations to get the individual eta I. And once you have the individual eta I of t, you can plug into this equation to get x of t. If you know eta of t, you know x of t. Okay. Step 4, compute x of t equals v times eta of t. Having computed eta